Kalispera from Athens, Kalimera, I suppose, some parts of the United States. Good afternoon in Boston, I suppose. Thank you all for attending this last session of CYA's virtual lecture series for 2020. When we first announced this idea, and we started broadcasting these lectures in June, we all had our reservations about whether this would really be of interest to a community and let alone become a success. And here we are, six months later, having done 10 episodes, 10 lectures, which have all been very successful. And they help us stay in touch and connected with our community, with our former students, our alumni, our faculty, former faculty, our friends, our trustees. The words of encouragement we get after each lecture and the queries we get can attest for this success. Now, it's heartwarming to scroll through some of the written messages on the Zoom platform and during the lecture and see along with the questions, all the excited reactions of former students who recognize their classmates and so on. And this is really the purpose of all this, is to keep this community together. Because this year has brought us so many unexpected issues, surprises, unscheduled circumstances, we decided that for our last lecture of 2020, we will present to you a subject which is very much not part of the academic curriculum of CYA. It has nothing to do with our offerings. It has not to do with ancient Greece or with modern Greece or the Eastern Mediterranean. We are going to look up to the sky and try to escape from COVID by visiting the cosmos. The topic of this discussion today is discovering the universe. It gives me very much pleasure to introduce our guest speaker, Dionysis Simopoulos, an astrophysicist, Director Emeritus of the Eugenides Planetarium in Athens, and an active spokesman for science education in Greece. And our discussant is Catherine Vanderpool, an archaeologist, an emeritus member of the board of the Eugenides Library of the American School of Classical Studies at Athens, and a former CYA professor. Before I go into their credentials, I believe it is essential to mention here that both of them are connected to CYA in a rather unusual way. Besides being good friends of the school and besides being good friends of each other, which we discovered recently, each of them is a parent of a staff member or a faculty member of CYA. Dionysis is the father of our development officer and behind the scenes planner for these virtual lectures, Billy Simopoulos. And I must say here that if it wasn't for Billy, these lectures would not be taking place. Really, it's his labor of love, and he does it with a great finesse. Kathy is the mother of CYA instructor Jeff Vanderpool, who teaches at CYA a course on photography and archaeology. So I may add, this is somewhat of a family affair this time. Now, Dionysis Simopoulos studied communications and astronomy at Louisiana State University in Baton Rouge, and his career began in the fall of 1967 when he served as assistant curator for education and later as planetarium director of the Louisiana Arts and Science Center. In 1973, he was invited to become the planetarium director of the Eugenides Foundation in Athens, Greece. I don't know if this was the first time this operation started its work. I believe it was. Dionysis can tell us later. His combined talents of science knowledge and communication ability have allowed him to write and direct more than 500 half-hour network television science shows and 200 multimedia planetarium shows, while publishing hundreds of articles in Greek and foreign magazines and newspapers. He has authored 31 popular astronomy books and has given more than 600 lectures on science communication throughout Greece. Simopoulos has served as president of the European Association for Astronomy Education in the 90s, as a member of the Executive Council of the International Planetarium Society from 1978 to 2008, almost 30 years. As Secretary General of the European and Mediterranean Planetarium Association from 1976 to 2008. And he's a fellow of the Royal Astronomical Society in the UK and the International Planetarium Society, and also a member of many other international scientific organizations. In 1996, he was honored with the highest International Planetarium Society Award for his contributions to international astronomy education. And in 2006, he was honored with the Palme Académique of the French Republic. In 2012, the Union of Greek Physicists honored him as the founder of the popularization of science in Greece. And in 2015, he received an award for his overall contribution to the popularization and dissemination of astronomy and space science in Greece. That was a citation, an award from the Academy of Athens. It is a pleasure and honor to introduce him and to have him here with us today. Dionysis will be joined virtually, as we said, with our friend Catherine de Gracia Vanderpool, who will serve as our discussant for today's lecture. Let me say a few words about Kathy. While a graduate student at Columbia University, she came to Greece as an associate member of the American School of Classical Studies, and that was in 1970. And after completing her PhD in 73, she settled permanently in Greece until 1986. She raised her family here, and she taught for several years at college here in Athens. And she also taught at the Center for Creative Arts, the Athens Center for Creative Arts. She served as editor and co-publisher of the Athenian magazine. Some of you may remember the Athenian magazine. It was a very fine publication. And she was writing, editing, and producing special publications, especially for the tourist industry in Greece. After returning to the US in 1986, she worked for the American School of Classical Studies office in Princeton. And she served for many years as the executive vice president and president of the Eugenides Library until she retired. She also served on the board of directors of the Council on American Overseas Research Centers in Washington, DC, including 7 years as chair. Currently, Kathy is an emeritus member of the Eugenides Library. She has written, lectured on Greece and on Greek history and art and archaeology for scholarly and lay audiences alike, and her current research interests are on Greek and Roman sculpture. And she's working on several publications now in connection with American School of Classical Studies excavations in ancient Corinth. Before I pass the floor to her, may I remind you again that this session is being recorded and the discussion will be saved for archival purposes by CYA. So those of you who prefer not to be on record could switch off the video cameras. Kathy, could you take over? Thank you.
Pleasure. Thank you very much, Alexis, for your kind introduction. And it's a great pleasure and honor to be here today, returning to the CYA fold after so many years. And I'd like to thank you, Alexis, and Billy Simopoulos for making it happen. And although these past 9 months have been extraordinarily difficult for all of us, one very bright light has been the birth of initiatives like this virtual lecture series. And while I look forward to a time when we can all be together again in Greece, hopefully, I do hope that these virtual connections will continue as well. My link with CYA goes back to the 1970s, when I had the privilege of meeting the legendary Mrs. Ismini Philaktopoulou, who invited me to teach a course on Greek sculpture. In retrospect, it seems a bit of heaven to have taught the great works of Greek art on site and to such bright and motivated students, and to have played some small role in introducing them to Greece. And by the way, if any of my former students are here today, I send you my warmest greetings. It was another lucky confluence of events that brought me together with today's speaker, Dionysis Simopoulos, and with his wonderful family. In the 1990s, Mr. Simopoulos and I, along with the late Daniel Borston, who was Librarian of Congress, were guest lecturers on a cultural cruise ship. Dr. Borston and I had the day shift, and Dionysis ruled the night. He was and is a riveting and gifted teacher. And each night he enticed crowds from the ship's less exalted entertainments and enchanted them with his knowledge of the stars. In more recent years, our paths crossed again at the 10th anniversary of the Digital Planetarium at the Eugenides, when Dionysis invited me to write an essay for the occasion. And as always, he was the best of colleagues, stimulating, imaginative, encouraging. And as you've already heard, he's had a career-long association with the planetarium. Its success today owes much to his passion for his science and to his vision that it should be accessible to and understood by everyone. Now, before turning to the lecture, I'd like to go over a few administrative details. Throughout the presentation, please feel free to submit your questions in the chat box at the bottom of your Zoom screen, and we'll get to as many questions as possible after the lecture. Today, Mr. Simopoulos will talk about recent developments in mankind's eternal quest to understand the mysteries of the universe. An archaeologist, eyes on the ground or near to it, attempts to weave a story of human history from fragments of matter that have been shaped by human hands. The astronomer lifts their eyes to the sky and explores matter of a different kind and a different scale, shaped by forces that continue to challenge our understanding. And it's this exploration which is the subject of today's talk, Discovering the Universe. Dionysus, over to you.
Wow. What an introduction. Both, thank you, Kathy, and of course, Mr. Philaktopoulou, for the invitation. Let me share, let's see. Yes. All right. Well, thank you very much for those, nice introductory remarks. I appreciate both of you. And of course, I appreciate the invitation. Because nowadays, because of the virus, I do not have a chance to talk as much as I used to. In previous years, especially after my retirement, 2014, I had something like, maybe 30, 40 lectures per year. So, with the virus that has gone down to only about 3 or 4 in the past 8 months or so, through, of course, through the internet. Anyway, in this lecture, I'm going to try to very shortly provide you with an idea of how and what we have discovered over the past 50 years or so about the universe. Of course, this connection, this connection of man to the sky and to the universe in general is not something new. It has been going on since ancient times, I guess, from the first time that man walked up on this planet of ours. And this appreciation that man has had about the sky and the universe has given him the opportunity to ask questions, where we're coming from, where we're going in the future, to ask questions, what is out there, especially during the night when they saw the first little lights, the moving lights of the planets, and of course, the big light of the moon, and of course, the little stars that are all over the nighttime sky. As Aristotle used to say 2,300 years ago, "O anthropos to ιδέναι οργέται φύση." It is in man's nature to want to learn. And this tendency of man has been continuing on from the ancient times to the present day. Maybe it's something that is deeply rooted in our genetic structure that guides us to search for the answers to our questions about the universe. And of course, the last 400 years, ever since Galileo in 1609 turned his little optical tube, as the telescope was called at the time, to the sky, and he saw the billions of stars making up the edge of the galaxy. He also discovered the 4 largest moons of the largest planet of Jupiter, proving in this way that the Earth was not the center of the universe. Of course, today's optical telescopes throughout the world on top of mountains are quite bigger than the ones used by Galileo 400 years ago. And as a matter of fact, right now, 2 of the largest telescopes are being built, one in Latin America, in Chile, and the other in Hawaii, with diameters of mirrors that reach about 30 meters, the one, and 40 meters, the other. So we're talking about huge strides in optical telescopes on the top of the surface of the Earth. And since the 1930s, and especially since the 1950s, a new window was opened to us with the help of a new instrument, the radio telescope. With these telescopes, we opened up new ideas about what is happening out there. Of course, most of the electromagnetic radiation that comes from the universe, the gamma rays, X-rays, ultraviolet radiation, does not reach the surface of the Earth, thankfully, of course, because of the Earth's atmosphere. And this, of course, is helpful to the life on the Earth, because this way we are protected from these harmful rays. So from the 1960s and afterwards, we have sent up in space our orbiting observatories. This way, we have gathered all the information from the electromagnetic spectrum, gamma rays, X-rays, ultraviolet radiation, of course, optical rays, and everything else has been given us a new view of the universe. We have seen, in other words, the universe with different eyes that could see information that was previously not available to us. And that was not enough. We sent our ambassadors throughout the solar system to all the planets, the satellites, the comets and asteroids that exist in our in our neighborhood of the solar system. And we took pictures and information that were not available to our Earth-based telescopes. And if you ask me if that was the only things that we did, no. We continued actually with thousands of satellites that are in orbit right now around the Earth. And we do not look only towards the universe, but we also look down on the Earth. And this way, all of our activities have been influenced by this space research in agriculture, in telecommunications, in archaeology, even in medicine and architecture. All of these activities were influenced by our space research. And, you know, sometimes most of us do not think that every day, each and every one of us, we use 50 to 60 different items that comes from our space activities, that comes from space research, things that in our everyday life, in medicine, and of course, in our human endeavors here on the planet Earth. And what we have learned all these years, actually, it's a tremendous, exciting amount of information. If we could put all the knowledge we had about the universe in the 1960s, when I was also in the university, if we could put all the knowledge we had about the universe in the 1960s in one book, in one tome, then today, 50 years later, our knowledge about the universe is so much bigger that we would need a library of about 1.2 billion volumes. So you can see that in 50 years, we have learned a lot about the universe. And since you are wondering what is an astronomer doing with a school that is concentrating in archaeology and in ancient times, I can tell you that us astronomers are really the archaeologists of the universe. Because when you look up in the sky, when we see all the various items, the various objects and the phenomena in the universe, we actually are studying memories. They have already happened a long time ago. Let me make it clearer. The closest star to us is, of course, the sun. It is only about 150 million kilometers away. But when we look at the sun, actually, when we see the light coming from the sun, we think that we see the sun exactly at the moment we are looking at it, or when we are looking at the rays that are hitting the surface of the Earth. Actually, that's not true. We see the sun as it was 8 minutes and 19 seconds before, because the light from the sun takes about 8 minutes and 19 seconds to reach us from where it is to the Earth. And that's the closest star to us. The next closest star is a triple star system in the constellation Centaurus. It is called Alpha Centauri. It's the brightest object in the constellation Centaurus. It is composed of 3 stars. The biggest stars are A and B. And of course, a smaller star, which is actually closest to us, closest to the Earth, is called Proxima Centauri, for obvious reasons. Well, Proxima Centauri is 40 trillion kilometers away. That means that we see that star as it was when we are looking at it tonight, as it was 4 years and 4 months ago. How it is today, how it is this star right now, we will have to wait another 4 months and 4 years and 4 months in the future. And of course, that's why when we're talking about astronomical numbers, when we're talking about distances in the universe, we're using not kilometers anymore, but what we call a light year, where a light year is the distance that a beam of light is covering in 1 year, running, of course, at the speed of light, 300,000 kilometers per second. So during that year, this light beam will cover a distance of about 9.5 trillion kilometers. Well, these 9.5 trillion kilometers, we call it a light year. So let's take another star called Vega. Vega is the brightest star in the constellation Lyrae, the Lyre. And that's why we call it also Alpha Lyrae. This star is 25 light years away. So when we are looking at Vega tonight, actually we're seeing how that star was 25 years ago. The most distant object that we can see with the unaided eye, without telescope, without binoculars, it's a galaxy in the constellation of Andromeda, and that's why we call it the Andromeda Galaxy. Well, that object that we can see with the unaided eye, it's 2.5 million light years away. We see it tonight as it was 2.5 million years ago. So you see, that's why we are called the archaeologists of the universe. The most distant galaxy we have recorded ever, it was photographed on the 3rd of March of 2016, 4 years ago, about. It is 13.4 billion light years away. So we see it as it was 13.4 billion years ago. That is 400 million years after the birth of the universe. And of course, our galaxy, the galaxy where the solar system and our planet is situated, is not that small. It's quite big. You can see where the solar system is situated. This arrow shows that we are in this particular point in space. We are about 26,000 light years away from the center. So when we're looking at the center of the galaxy, where, by the way, there is a big black hole over there, when we are looking at this black hole or the surrounding of the black hole, we see it as it was 26,000 years ago. From edge to edge, this galaxy of ours is 100 million, 100, these numbers are really astronomical. From one edge to the other, this galaxy of ours is 100,000 light years. In other words, if we had a spaceship that would run at the speed of light, 300,000 kilometers per second, it would take that spaceship 100,000 years to go from one side of the galaxy to the other. A galaxy which is an average galaxy of about 100 billion stars. Now, if you ask what does 100 billion means, it means that if you wanted to count all the 100 billion stars in our galaxy without doing anything, without eating, without sleeping, without doing anything except count the stars, it will take you 24 hours a day. It will take you about 3,500 years to count these 100 billion stars of our galaxy. And this is one of about 50 galaxies that compose our local group of galaxies. This local group of galaxies is actually, there are three large galaxies in our local group. The Andromeda Galaxy, our Milky Way Galaxy, and another one towards the constellation Triangulum, and about 50 other smaller galaxies in our local group. And this local group of ours belongs in a larger supercluster of galaxies towards the constellation Virgo, and of course the name Virgo Supercluster. And of course, this supercluster is not the only one. We have dozens of local superclusters of galaxies in the universe that composes the universe. And altogether, if you want to count the galaxies in the universe, the latest count is about 1 trillion galaxies. Now you can imagine how long it will take you to count just all these galaxies. And about 90 years ago, an American astronomer, Edwin Hubble, discovered that all these galaxies are flying away from us. They are flying away from each other. In other words, we are talking about an expanding universe. As a matter of fact, during the 1920s, in 1927, a Belgian astronomer, Georges Lemaitre, said that if really this is an expanding universe, if we bring back all these galaxies that are flying away, then we would reach the center or the beginning of this explosion of galaxies, which he calls a cosmic atom or a cosmic egg. As a matter of fact, this Big Bang theory started in the 1920s, and of course it developed, and in 1948 or so, in the 1940s, George Gamow and his collaborators realized that if really the universe was born in a Big Bang, then there should be the remains of the radiation of that huge explosion. A radiation, of course, that today has cooled off, and it has become what we call the background microwave radiation. And in the 1960s, 1964, 1965, two engineers working at the Bell Labs, Penzias and Wilson, discovered that, actually made a portrait of that microwave radiation. And this is the first image, actually the first portrait of the universe after it was born. For this discovery, even though it was accidental, they got the Nobel Prize of 1978, Nobel Prize of Physics in 1978. Later on, in the 1990s, 1992, with the help of 1,000 collaborators, two researchers sent into space in orbit around the Earth, a spacecraft called COBE, which actually made a better portrait of the early universe, for which, of course, they got the Nobel Prize of Physics of 2006. Later on, in the 1990s, with the help of the European Space Agency's Planck telescope, we have a much better portrait of the universe as it was 380,000 years after the Big Bang. Of course, everybody would wonder that this 380,000-year-old portrait is not by any means the beginning of the universe. Actually, we cannot see with our telescopes or other instruments, we cannot see the beginning of the universe because there is a cosmic fog that does not permit us to go back. In order to go back to the first moments of creation, we have to go inside the atom smashers, super colliders, such as the one that exists in CERN in Switzerland, and of course Fermilab in Illinois, Brookhaven in the United States. Actually, inside these super colliders, what we see uh, a, an imaginative sort of recreation of what happened the first trillionth of a trillionth of a trillionth of the first second. What we know for sure is that at that moment, about 13.8 billion years ago, the first 3 minutes of the universe's existence, all the hydrogen that exists in the universe ever since and today was created in the first 3 minutes. Actually, all the rest of the chemical elements are being produced inside the stellar nuclei, inside the stars. And since a human being is composed of atoms, as a matter of fact, a number of atoms equal to about 7 billion atoms in one human body. And because 62% of the atoms in us is hydrogen, that's why we say that 2/3 of our bodies has an age of 13.8 billion years. We are stardust, as so aptly Carl Sagan used to say some years ago. And of course, all this electromagnetic radiation, which is our main source of information about the universe, is gathered with the help of the electromagnetic radiation observatories, telescopes on the Earth and in space. Thus, with all the knowledge that we have gathered over the past 50 years, we have created a model. We call it the Standard Model, that puts together 3 of the 4 fundamental forces, all the particles that compose matter, and all the particles that compose the various interactive forces are put together in this Standard Model. As a matter of fact, one special particle, the Higgs boson, was not discovered for practically about 50 years, since the 1960s, early 1960s, when Peter Higgs, a Scottish physicist, first made a mechanism to give the mass of all the particles, the way that the particles get their mass. But we could not find it until July of 2012. And of course, Peter Higgs and his collaborators got the Nobel Prize for Physics the next year, 2013. But as I said, this Standard Model comprises only 3 of the 4 fundamental interactions. The 4th one, a very special and very important one, gravity, is very weak. It is 100 trillion times weaker than the electromagnetic interaction. And yet gravity is very important. The only theory of gravitation, well, actually the main theory of gravitation we have about gravity is the general relativity of Albert Einstein that was presented for the first time in 1915. Among the various predictions that general relativity had was the existence of gravity waves when we had the motion or the movement of huge masses like black holes or neutron stars. Then this motion, this movement, create gravitational waves. But because gravity is so very weak in comparison to the electromagnetic interaction, actually we could not, up to recently, up to about 5 years ago, we could not possibly detect these gravitational waves until the 14th of September of 2015. We did detect these gravitational waves. What this signal told us, which was officially announced on the 11th of February of 2016, was that what happened 1.3 billion light years away, or 1.3 billion years ago, it was that two black holes, one with 36 times the mass of the sun, and the other 29 times the mass of the sun, collided. And by colliding, they formed a bigger black hole with a total of 62 solar masses. Actually, 29 and 36 is 65 solar masses, but the three solar masses that are missing from this black hole was in a moment a part of 1 second were produced huge amounts of gravitational waves equal to 50 times the energy of all of the galaxies of the universe. Ever since, of course, we have seen many more such gravitational waves between the collision of two black holes, or the collision of a black hole and a neutron star, or the collision of two neutron stars. And we have opened up, in other words, a new window to the universe. So with the help of our instruments, we have learned a lot about the help of the various telescopes on the surface of the Earth and in space, with the gravity laboratories, the LIGO laboratories, one that exists in Louisiana, very near Louisiana State University, the other 3,000 kilometers away in the state of Washington, and of course, lately, a European one near Pisa in Italy, in the northern part of Italy, called VIRGO. These are the new instruments that help us understand the universe. So we have learned a lot. We have learned how the solar system was developed. We have learned the life cycle of the stars. We have learned the history of the universe. We have learned a lot, but there are still many more that are unknown to us. For example, we don't know what the so-called dark matter is composed. And yet this dark matter is very important to the existence of our universe. We don't know what we call dark energy that causes the universe to expand accelerated. We have an accelerated expansion the last 6 to 7 billion years now. Of course, they got the Nobel Prize for Physics of 2011 for that discovery, because it was really an eye-opener of about 20 years ago. So if you ask me today, what is the composition of the universe, I would say that 27% is made up of dark matter, which we don't know what the heck it is. 68% is made up of dark energy, which we do not know what the heck it is. And all the billions and billions of galaxies that we see up to now, all this matter, the ordinary matter we see, is making up only about 5% of the composition of the universe. So we think that we know a lot, and yet the more we study the universe, the more we realize that we do not know as much as we think we do. So now we are sitting on a small planet around a small star, in a small galaxy, really, in the universe. We are sitting at the seashore of the universe, and we realize that really we do not know as much as we thought. Well, thank you.
That was fascinating, illuminating, awesome in the sense that I am in awe of the accomplishments, the achievements of 60 years of human endeavor. It's how can I say, well, it would require, I don't know how long it would take somebody to go through all those books you said that have been produced in the library, the enormous library of books that has been produced in the last 60 years on this field. Extraordinary.
But don't forget, Kathy, don't forget that what Newton used to say about 350 years ago, when he said that if I was able to see more than our fellow men, I was able because I was sitting on the shoulders of giants.
Yes.
And therefore, really, today's accomplishments are being built from the accomplishment of the past.
Mm-hmm. And it's also humbling to realize how much we do not know. And maybe we can't know. I don't know. Anyway, I know that people will have questions, and I see some already in our chat box, but I'll start off with one or two of my own. What was there before the Big Bang? Before
the beginning of time.
Is that a theological question, or is it?
Well, it's a logical question with the sense that everybody wants to find out what it is before, but it does not really make sense in the sense that before the existence of time, we cannot go back. It's similar to some colleagues of mine have used the example of what is north of the North Pole, northern than the North Pole. Well, the South Pole, I guess. So in actuality, we do not know. I do not think that we could possibly go in that position, not even just at the time of zero, the beginning of the universe. It is a place that really science, current science, has not been able to even theoretically go to. So before the Big Bang, well, we don't know.
Sort of related, could there be other universes besides our own?
Oh, there are theories about it, yes. But you have to realize this thing. There are theories that tell us that on the first trillionth of a billionth of the first second, we have the creation of a number of parallel universes, which is the number one followed by 506 zeros. That's how many parallel universes there exist. But in order to prove the existence of such universes, then we have to do it in our universe. We have to see the proof. We have to watch for the proof of the existence of these universes in our own universe. So if we can do that, then we can prove it or not. Because, you know, astronomy and science in general will have to have either by experiment or by observation, we have to prove our theories. You cannot just get up and say this or that without proving it.
So I'm looking at the chat box, and we have a number of thank yous and wonderful complimentary comments. Let's see. From John Pazares. John says, my daughter wants to ask you, you said that we don't know what dark matter is, but do we know what it is not?
That's a very good question. Actually, neither. We do not know what dark matter is or what dark matter it is not. What we do know is that its existence is revealed to us by the influence that dark matter has on the galaxies that we see. We see that there is something there that influences the existence of the galaxies and the stars. And that's then we infer that it would be something like 5 times the ordinary matter in the view of dark matter.
And I think we have time for, I don't see any more questions in the chat box. I do have a question from my 10-year-old grandson who wants to know the future of manned or womaned space exploration.
The future is going to be glorious, but it is not going to be as fast as some people think. For example, we see Elon Musk, for example, Jeff Bezos, other entrepreneurs who are putting a lot of money, billions actually of dollars, in space exploration. And they think that as early as the late 1920s, 2020s, the next 10 years or so, they will be able to send a human crew to Mars. Well, I'm afraid that that will not happen. I'm afraid that all of the attempts that will happen in the next 10 years, it will be in our neighborhood. We will reach the moon for another time, just like we did 50 years ago. But the moon is very close to us. It's only about 400,000 kilometers away. To go to the moon, it will take, with current technology, about 3 days to go there, 3 days to come back. In a week, in other words, you will have a round trip to the moon. But in order to go to Mars, you have to wait for more than 2 years, actually. It takes about 6 to 8 months to go and another 6 to 8 months to return. And you have to have the 2 planets to be very close to each other. So actually, going to Mars is not going to be as easy as some people think, or as inexpensive as some people think. I believe that going to Mars, a human crew to go to Mars will take another 50 or 60 years. But of course, in the meantime, we would have been able to return to the moon by 2024, 2025. Already, the European Space Agency, NASA, in the United States, Japan, even the Russian Space Agency and the Chinese Space Agency have already laid plans to return to the moon. So the 2020s, the next decade, in other words, will be the decade of returning to the moon, forming our first laboratories on the surface of the moon. But going further out, like Mars, will take a few more decades.
Thank you. And one more question, because we're close to pretty much at the end of our time. This is from E. Holmes. What is the difference between dark matter and antimatter?
Oh, it's quite different. Antimatter is very well known to us. It's the opposite of the ordinary matter that we see. Well, the only difference between ordinary matter and antimatter is opposite electrical charge. In other words, the electron has negative electrical charge. The positron, antimatter, the equivalent particle, has a positive electrical charge. So actually, we understand antimatter very well. The trouble is that when we have a particle of antimatter coming and shaking hands with a particle of matter, well, they annihilate each other, turning into energy. And therefore, matter and antimatter is not going to happen. Now, the question is, why? Why we have a universe made up of 99.99999% of matter and not equivalent antimatter? Because that's one of the big questions, this difference between matter and antimatter. Now, on the other hand, dark matter is quite different. We don't know anything about it. So we see the influence it has on ordinary matter, but that's about it.
I said, I said that we would have, the last was our last question, but then I just see a question popped up from my son, and I can't say no. So you have
Are
patience.
you talking about Jeff or Nick?
I'm talking about Jeff.
Okay.
So if I may, Jeff says, I remember a folk tale explaining the universe where a wise man said that our world is riding on the back of a tortoise. Asked what the tortoise is walking on, the man said, it's tortoises all the way down. So I ask, is there an edge of the universe or does it go on forever?
Well, that's an excellent question, actually. I'm not going to touch, on the ancient idea, which of course it's a Hindu idea that, the turtle, yes, on top of the turtle, you have elephants and so forth and so on. And below the turtle is the universal snake. Anyway, I'm not going to touch that. It is not in my belly weight or something like that. So I'm going to touch on the real question. Is there an edge to the universe? Like I said, we're talking about the observable universe. And the observable universe has an edge. In other words, it has all the information that we can get, all the information that gets to us. Now, beyond that, we do not know. We estimate that it is probably an infinite universe, probably a universe that goes on and on and on. But there is an edge as far as we are concerned, and that edge we call the observable universe.
Lovely, wonderful. Well, thank you for a wonderful presentation and for handling the questions so beautifully. I look forward to a time when we can get together in Greece. And before I turn the microphone back to Alexis Philippopoulos, I'd just like to wish everybody a wonderful holiday, as happy as possible, and may our new year be healthier and happier for everyone. So, Alexis.
Thank you. Thank you, Kathy. Thank you, Dionysis. Fabulous talk. When you were off the screen, we resorted to something a little bit more mundane, and Kathy asked me, what would be a very romantic question. Where would you look at the stars more easily in a clear night? Where would you get better sight of the stars? In Attica, she said. So I wasn't quick on my feet. I should have said, of course, there are two places in Attica where that could happen, I suppose. One is the largest uninhabited island in Greece, that's Makronissos, which is right off the coast of Sunion. And but how do you get there? I don't think there's a ferry gate taking you to Makronissos, but that's uninhabited and it's far from any lights. And then the other, I would imagine, is on top of Mount Parnitha. If you can go up there, I don't think there are any lights around there. Anyway, Dionysi, thank you so much. I want to relate an anecdote that you told me before, which was that when you came here to Greece at the age of 29 and you started working here, an older professor from Athens said to you, well, if you speak very simply, people will just say that you're not smart enough. If people understand what you're saying, they will think that you're not smart enough. If you talk above their heads, well, they will obviously start respecting you more because they won't be understanding what you're saying. Well, thank goodness you didn't take their advice, and you have learned the art of making a very complex subject approachable to laymen, to children, to students. You help everyone understand and learn something about the solar system and the cosmos in a wonderful way that only you can do it. And you exhibited this capacity today. Thank you very, very much. Anyway, I want to thank you and the audience for attending this tonight and for their participation. And again, my wishes for lovely holidays, safe and out of trouble. And we will be back with more of our lectures right in the beginning of the new year. Thank you very much and good night. Bye-bye.
Thank you.